how to find omega, which is omega n, which is the natural frequency, and the zeta from a given transfer function. For example, if the transfer function is like g of s one over 2s square plus 16s plus 400. I believe you have seen this over here. Let me see. Yeah, this is the 1 over 2s square plus 16s plus 400. So I'm interested in finding out the properties zeta and omega n from this transfer function. So how will I start with? I will start with a standard second order transfer function. And what I mean by standard, this means this one. So suppose this is a natural frequency in the numerator square, and s square plus 2 zeta omega n s plus omega n square. Now, in order to find out this zeta and this omega n, we have to convert our actual transfer function in this form, in the form of a g1s. So let's do some rearrangement. This is my actual transfer function, and you see the coefficient of s square term is 1 in the standard, but coefficient of the polynomial in the denominator is very important. That's known as a characteristic polynomial, and the s square term is not 1. We have to convert it into 1. So how will I do that? I will just bring this common, s square plus 8s plus 200. This is very simple. The next step I want to see, over here I have omega n square and the numerator the same number. Alright, so how will I bring the same number? I have 200 here, I must have 200 here. In order to have 200 here, I would divide it by 200, and now this thing is in the standard transfer function form, and remaining thing is just scaling factor. So I can rewrite this actual transfer function in this way: 200 over s square plus 8s plus 200. So now it is very convenient for me now to exactly define what is this omega n squared, and once I know omega n squared, so I can just write down square root of 200 is equal to the natural frequency. This is in radians per second. This is my natural frequency. So the objective of this transfer function, from the transfer function, how to find out the natural frequency, how to find out the zeta. So now the next help from the standard function is the coefficient of the displacement, coefficient of the s term, which is 2 zeta omega n. So let's compare with the actual. What is the coefficient of our actual transfer function? 8. This gives me another equation. So 2 is cancelled by 4. 2 4s are 8. So that means zeta equals to 4 divided by 14.14. So let me do the math here in this calculator. Divided by 14.14. This is my damping ratio. It is unitless. So have you guys understood how to find out zeta and omega n from the given transfer function. And once you know these two values, then you can find out the rise time. Rise time is 2.2 the time constant. You can find out, first of all, find out the time constant, which is equal to 1 over zeta omega n. Then find out the rise time. Then find out the time to reach the first peak, which is pi over omega d. And omega d is the damped natural frequency, which is 1 minus zeta square. And maximum overshoot, which is pi zeta or 1 minus zeta square. The answer would be in decimal, so you will multiply by 100 to find out the answer in percentage. How much percentage? So this is the step, so this is the overshoot, this is, so the first peak time to reach the first peak, this is the MP, this is the rise time from 10% to 90% of the set value and so on. And this is settling time. Settling time is the time when the set value has been achieved. 98% of the set value is acquired in the settling time, and settling time, the formula is 4 times the time constant, and that is equal to 4 over zeta omega n. So let's do this one by one. What is this? 1 over, so I would write down 0.2829 is my zeta times 14.14 raised to power negative 1 is 0.25 seconds. So this is how you will find it out, and remaining I will leave it to you to do this by yourself.